Now, we are going to look at in this section different transport coefficients. So, let us look at your slide where I describe different kinds of coefficients. So, if you look at temperature difference leads to the heat flow from high temperature to low temperature, that is one of the transport of the heat flux. If you look at the pressure differences cause mass flow, that means there is a mobility of the particles. So, high pressure to lower pressure, this is where the fluctuation is going to happen, and as it dissipates over a period of time, we want to look at fluctuation dissipation. So, if you look at transport coefficient, essentially describe relaxation or dissipation response of the fluid to an external perturbation. So, if I perturb a system, move it somewhat in terms of temperature or pressure, then there will be a response to that, there will be relaxation of that perturbation over space and time, and that is what we are looking into transport coefficient. And if you look at Green-Kubo, describe the transport coefficient in terms of time correlation functions. So, if you look at Green-Kubo formulation for the time correlation function, which you had seen earlier, that is where we are now going to start with the time correlation function first before we go to space time correlation functions. So, I want to make sure you differentiate between the time correlation function, which are essentially leading to what we call is mean square displacement. You start with the self correlation of the particle from time t0 when it started to various different time intervals at any arbitrary time t later on. So, we are looking at now particles moving over the period of time, and then we are correlating the initial position with the position at time t, and we are collecting the statistics over n number of such time steps using molecular dynamics, because we are able to calculate the trajectory of the particle. So, we know at any time t where they are. So, if you look at mean square displacement, then we are now going to look at Green-Kubo formulation for mean square displacement first, which will lead us to the calculation of diffusion constant, which is one of the transport coefficients. Just like thermal conductivity is one of the transport properties, diffusion constant is another such property. So, let us start with Green-Kubo. So, let us look at our formulation here on your screen. So, you have mean square displacement, which is defined r, which is the position at 0 time and at time t, and we are doing mean square displacement. So, we are averaging, which are these brackets which say that it is averaged over time, but it is mean squared. So, it is the square and the mean of all of those square displacement is collected. So, if you look at we can also look at in terms of the displacements and the velocities in terms of the if the particle has a velocity, then you will find out at time t what is its location, what is the position. So, then integral from 0 to time t, and if you integrate over v time t dash, now you can calculate mean square displacement in terms of velocity correlation. So, now we are integrating r t minus r 0 square as integration of from 0 to time t, and so we are looking at two integrals here at time t dash and at time t double dash. So, if you look at these velocity correlations, so t dash is the initial and t double dash is some other time dependence. So, we are also looking at velocity correlation there. So, now because of the time translation invariance is at the system at equilibrium. So, when the system goes in equilibrium, the time translation is invariant. So, we now can apply the invariance from the time velocity at time 0. So, if you look at time t dash minus t double dash any arbitrary times, and if we then correlate it with the time velocity at time 0, that is where we come up with the velocity autocorrelation. So, now we have a good understanding about mean square displacement being a integration of 0 to time t, because we are doing double integration here. So, and looking at the two time intervals, now we have from t minus t dash, and now we are multiplying that with the correlation which is the velocity autocorrelation. So, with that if we solve that equation, then we know in terms of velocity v 0 6 v 0 square. now we have t d dash and we have psi t dash, which is essentially velocity autocorrelation connected with the mobility of the different particles. So, if you look at the mobility of these particles, and the velocity autocorrelation is a normalized velocity autocorrelation, and so that is where we are able to now calculate the mean square displacement from the Green-Kubo formulation. So, Green-Kubo formulation is essentially equivalent to looking at the velocity autocorrelation, multiplying that by the mobility of the particles and their velocities, and that is when you get a formulation at for the Green-Kubo formula, and that leads to now the diffusion constant, because now we know mean square displacement and diffusion based on the Einstein theory of diffusion, it is 1/6 of the mean square displacement averaged over time. So, if you look at d is equal to 1/6 of which is called self diffusion coefficient is related with mean square displacements, and because we know mean square displacement is equivalent to a velocity autocorrelation. So, now we have diffusion constant calculated using velocity autocorrelation function. So, this gives you a very simple Green-Kubo formulation, and Green-Kubo formulas are now connected with all kinds of correlation functions. So, this is the first one, which is based on the time correlation function, which comes out of the time of the velocities. So, this is where you understand that there is a formulation which Green-Kubo came up with in early 60s, which was essentially to connect autocorrelations and correlation theory with the transport coefficient, and that is where you look at the what we call as dissipation, fluctuation dissipation. So, if I fluctuate a system, perturb a system, it is going to settle down, and if we look at the time trajectory of that perturbation and see how it dissipates over time, then we can come up with a exponential decay model, and that will give you a lot of information about time correlation, and that time correlation then connects with the transport coefficient. Physically speaking, I think you can think about transport coefficient you can measure under a perturbation, because once you perturb a system and you are looking at how the transport is happening, that is where you can figure out what is the coefficient of transport. And so, it is important that you create fluctuation, but the important thing here physically speaking is that the time correlation function or space time correlation functions are allowing you to calculate the transport coefficient, and that is important because these important transport coefficient, which essentially are very important factors for calculating any physical phenomena like hydrodynamics or like heat transfer or thermal fluid mechanics. In all of that you need transport coefficient, and that is where the question is that how do you use molecular dynamics. The good idea here is that molecular dynamics gives you the time steps, it gives you the time dependent variation of certain properties, and it also gives you the location of the particle. So, you can have space, which is the position change over time, and we can also look at other properties like velocity change over time. So, now you have space time correlation functions, and this is where we are going now to look at velocity autocorrelation, which also then connects you to not only the diffusion constant, which we look at, which was formulation by Frankel and Schmidt, which you can use in terms of connecting it to diffusion constant, and this is where we had looked at earlier, but now you understand the formulation is where we start with the definition of velocity autocorrelation, which connects with the definition of diffusion constant from the mean square displacement, and that is where you look at the property of the velocity autocorrelation function. And as we said, it is also a parameter that can explain to you the phase transition. So, if there is a simple decay, which is now we are looking at 3 different substances of velocity autocorrelation, if exponentially goes to the 0 value from a arbitrary value, let us say unity, that would be a gas phase, because in this case there are very simple correlation and almost it goes to the exponential decay. But if you look at the fluid properties, which have more correlated velocities of the particles as compared to gas, because gas is rarefied. So, if you look at the dense gas, there is hardly any correlation, that is why there is autocorrelation is decaying exponentially. But now, if you look at the fluid system, then it will decay fast, but at the same time it will bounce up and will go to asymptotic with the 0 value, that is a typical liquid behavior. And if it goes negative first and then fluctuates around 0 value, then you have a solid behavior, primarily because these are highly correlated. As the particles become highly correlated, you will see fluctuation, dissipation, and that is where the dissipation becomes almost like dissipated vibrational models, where you see the sinusoidal kind of behavior, which is a damped vibration. And damped vibration start with the large fluctuation first, and then it damps down with the smaller fluctuations later around, let us say, simple harmonic oscillation. So, oscillations start with higher amplitude, then they go to 0 amplitude, and that is the typical behavior for a solid, because there is dissipation in a very correlated environment. So, let me stop here. We are now going to look at the space-time correlation functions and see how we can connect that with some of our molecular dynamic simulations. Thank you.